Hey everyone, today we're talking about the Hindley-Milner type system. We're not going to spend quite as much time on the formal theory of semantic analysis and type system as we did for parsers and languages. The reason is, it's difficult to reason about parsers and languages, and it's really useful to have this theory. For semantic analysis, most of the challenges are engineering challenges. Nevertheless, there is some very good formal and fundamental work that has been done, and this work actually has practical applications. So I would be remiss not to talk to you about it. The Hindley-Milner type system, and you can see Hindley-Milner on the right, it's a type system for the polymorphic lambda calculus, which is also called system F. It is relevant in practice because it underlies the type system of Haskell and ML, and probably other languages also. Of course, the languages are much more intricate than the Lambda Calculus, which is an abstract toy language. However, the Hindley-Milner type system is still the core of the algorithm behind the type system of those languages. Let's refresh your knowledge on the Lambda Calculus. The Lambda Calculus is a set of expressions that look like this. So there are variables, there are function abstraction, so basically just function definition with one parameter, and there are function applications. Next, there is the simply typed lambda calculus, and the idea is to introduce types into the lambda calculus, and this takes the form of type annotations on the parameters of the abstractions. We also need to introduce constants. We will also need a set of base types. So for instance, the set B, which has the A and B types. The universe of types, so the set of all types that we can create in the simply typed lambda calculus, is made of the base types and all function types that can be made from the base types. So here, from A to the function type A to B. So why are the constants necessary? We didn't have them in the normal lambda calculus. The reason is that in the normal lambda calculus, you can represent things like numbers using functions. And you do that using something called church encoding. In the simply typed lambda calculus, because of the type annotations, the church encoding does not work anymore. And so you do need constants, otherwise your language does not have any object. You can never do function application because there is no value that inhabit the types. Finally, the polymorphic lambda calculus. The idea is to take the original lambda calculus and to have type for that without the type annotations that the simply typed lambda calculus introduced. And so this is the normal lambda calculus. And then we also have this extra let statement. We will explain later why that is actually needed in the polymorphic lambda calculus. We haven't really said what a type system is. Type system is a formal system or a formalism that determines for any expression in the language if the expression is well typed, and if the expression is well typed, what its exact type is. So let me give you an example. In the simply typed lambda calculus, this expression is ill-typed. And it's very simple. It's an abstraction with parameter of type A, and we apply it on a constant that's type B. So obviously, B to A, that's not compatible. So this is ill-typed. A few desirable properties of type systems. Decidability, which means that our typing algorithm can make a decision. It does not run forever and does not crash. Soundness, which means that everything that we can prove, everything the type system says is actually true. And completeness, which is that we can prove everything that is true. This doesn't seem like asking for much, but actually it is. We know from Gödel's incompleteness theorem that there is no sound system of axiom describing natural number arithmetic that can be complete. So natural number arithmetic, that's positive integers, and arithmetic means that we have multiplication and addition. That doesn't seem like too much to ask, and a sound system that describes that, so a system that only proves true things, cannot be complete, which means that there are statements about natural numbers that we cannot prove for any system. So this is one of the most earth-shattering results of mathematics. Of course, we are computer scientists, we're programmers, we're not mathematicians, and so we are also bounded by pragmatic considerations, which means that in practice, this does not always matter. For instance, Java is not any of those. It's not decidable, because you can actually write programs that will crash the compiler. This is arguably a compiler bug, and so it should be decidable. It is not sound because you can compile some programs that will always crash at runtime for type reasons. And it's not complete because there are things that are true in the underlying theory that cannot compile. In practice, however, it doesn't matter because the programs that exhibit these bad properties, nobody would ever write them. They are complete corner cases. Also, in practice, you probably want to get decidability and soundness. You don't want your compiler to crash or to hang forever, and you do not want to allow invalid program. Typically, what you will sacrifice is completeness. So there's going to be some programs that are well typed in theory that we're not going to accept. And once again, typically we're talking about corner cases. Before we discuss Hindley-Milner, which is a type system for the polymorphic lambda calculus, let us discuss the type system for the simply type lambda calculus, which is denoted by this symbol. So we have 4 inference rules, with one or multiple premises on the top and a conclusion on the bottom. You may notice the symbols in the rules. So gamma is a context, which is a set of type bindings, also called assignment or assumptions. The symbol here, that's called a turnstile, denotes a type judgment, and it's typically preceded by gamma. A type judgment is what gives us information about the types. And finally, sigma and tau are characters used to denote types. Let's start with the first rule. This says that if the type binding that x is of type sigma is within the context, then we have a type judgment of the same effect. This is just mathematical accounting. It just says that the context tells the truth about types. The second rule is similarly simple. It just says that if c is a constant of type t, then we have a type judgment to the same effect. Things get interesting in the third rule. So in this rule, we take a context, but then we adjoin a type binding that says that x is of type sigma. If we can show that using that context, then the expression e as type tau, then we can show that a function, or an abstraction, with a parameter of type sigma, and a body e as type sigma to tau. Sigma is the type annotation for the parameter. If we assume it, and if using another rule, we can show that e as type tau, then this does make sense. A function, we know the parameter type, and through the premise, we do also know the return type. So how do we get this premise? Well, we get it through some other rule. So for instance, e could be a constant. Then we could use rule 2 to say that whatever actually the parameter type is, the return type would always be the type of the constant. And then this is easy to type. Finally, we have the fourth rule, which is for function application. Here is an example of function application. So it says if we have an expression e1, which has a function type, sigma to tau, and e2, which has a type sigma. So in this case, this would be e1, and this would be e2. Again, how do we get this judgment from other rules? So in this case, I use a constant, so we would get the type judgment from this rule. This being an abstraction, we would get the type judgment from this rule. Once we have that, we can say that applying the function e1 to the value e2 as type tau. Well, this makes sense. e1 is a function from sigma to tau. You give it a parameter sigma, you get back a value of type tau. So none of this should be very surprising. These are the normal rules to get the type of function and to type the usage of function. To go towards the full Hindley-Milner type system, we can start by reusing the same rules. We only have 3 rules because the polymorphic lambda calculus does not have constants. Otherwise, it's pretty much the same. You can ignore the d after turnstile. That's because I took these equations from the Wikipedia page, and they have multiple formalization for the Hindley-Milner type system, and this is the declarative formalization. The only difference is that abstraction does not have type annotations, and this does have a very important consequence, which is that functions can have many types. So if you take this function here, it's the identity function. If you assume that x is of type int, this function has type int to int. If you assume that x is of type string, this function has type string to string, and so on and so forth. So why is it actually called the polymorphic lambda calculus? Polymorphism means many forms. And as we've seen, some function may have many types. But shouldn't they really have one canonical type? Can't we express the fact that this function works on all sorts of types? As a matter of fact, we can. We can use such a type here, and this is read as for all alpha, alpha to alpha, and this is a polymorphic type. So you can see that the universe of types in the polymorphic lambda calculus is divided between monomorphic types, which includes variable and abstraction. There's this here that you should ignore, that's used for other formalizations. And polymorphic types, which are either monomorphic types or quantified types. Now, why do we actually need polymorphic types? Here is an example. So this is a function application. So the first line is an abstraction, and the second line is also an abstraction. It's the identity function, and it's passed as a parameter to the abstraction on the first line. The body of that abstraction is not really important. It's that way so that it's syntactically correct. What is important is that it calls the identity function twice. It calls it once with an integer, and it calls it once with a string. Using the current rules, this can never work, because the parameter has to be typed before the whole application can be typed. And so either you will give it the type int to int, then you can call this, but you cannot call this. Or you will give it the type string to string, then you cannot do this application, but you can do this application. The hope is that by using a polymorphic type, we will be able to make this work somehow. For that, we will need new inference rules that actually include polymorphic types. So how do we actually introduce polymorphic types into the calculus? For this, we need an inference rule that allows us to give a polymorphic type to functions. This is the generalization rule here. What it says is that if we can infer that E has type sigma, and that the variable alpha is not free in gamma, and I will explain what that means, then we can generalize the type of E to become for all alpha sigma. So what does it mean for a variable to be bound? It means that it appears in gamma either as a quantified variable, so for instance, this variable is not free, or it appears in a function type, for instance here, but it must also never appear on its own. If you have a variable in gamma whose type is alpha, then you cannot generalize over alpha. Where do you actually get this variable from? Well, we get it from the abstraction rule. As we said, there are many functions, such as the identity function, that have many types. And that means that we can actually pick whatever type we like for those functions. For instance, for the identity function, we could have picked alpha for tau here, and so that gives us the type alpha to alpha from the conclusion. So that's the abstraction rule. And then we use the generalization rule to generalize that to for all alpha, alpha to alpha. So this is the first step. And if we take our example again, this means that now we can assign a polymorphic type to this function. However, what we cannot do is apply this function. Why? Because if you look at the application rule, the function has to be tau to tau prime, and these are monomorphic types, and there's no allowance for polymorphism there. So what we need is an inference rule that goes from the polymorphic type to a specialized type. And this is the instantiation rule. What it says is that if we have inferred that E is of type sigma prime, and we know that sigma is more specific than sigma prime, then we can specialize E to be of type sigma. So this notation here means sigma is more specific than sigma prime. It's a bit confusing because it looks like set inclusion, and the way I like to think of it is as a set of constraints. So the set of constraints of sigma is bigger than the set of constraints of sigma prime because sigma is more specific. So sigma includes all the constraints that sigma prime does. In practice, all you need to remember is that we use the instantiation rule to go from a polymorphic type into a specific type. And with that, we'll be able to instantiate here to an int type function and here to a string type function. And then we can actually use the application. Let's now talk about this let form that we have. And at first glance, it's very confusing because you might think that let x equals e1 and e2 would be exactly the same as this form here, which is passing e1 into an abstraction or the body is e2. The only reason it is not the same is that the application rule says that e1 has to be of type to. And if you remember, to denotes a monomorphic type. So before, when we did this example, I actually lied. Because sure, you can type this to a polymorphic type, but then you cannot do the application, because this does not satisfy the premise. It has to be monomorphic. However, and that's where let comes in, you can rewrite this to be like this instead. So now we say let id equals the identity function in the same body as before. And this does work because of the let rule. So the let rule says if we can infer that e0 is of type sigma, and if we assume that x is of type sigma, then we can infer that e1 is of type to, then let x equals e0 in e1 is of type to. The best way to think of the let rule is that it's the combination of the abstraction rule and the application rule. So this rule here is very similar to this premise here. And this premise here, for the value that gets assigned, is very similar to this premise here. And basically what the let does is that it plugs the conclusion of the abstraction into the premise of the application there. So it does both steps at once. The only difference, of course, is that it is able to handle polymorphic types, whereas in application we're stuck with monomorphic types. So why do we have this weird restriction? Why must application work only on monomorphic types? The reason is that if we do not put this restriction, then the polymorphic lambda calculus becomes undecidable. This is very undesirable. Remember that if it's undecidable, then a practical decision procedure might not terminate. As to why it is like this is beyond the scope of the course. It would be very difficult to explain. In fact, I couldn't explain it myself without doing some research. But it suffices to know that the reason that let exists is to do things like this. For this reason, it's sometimes known as let generalization, because using let lets you generalize function so that they may be called on arguments of different types. And so that's the whole of the Hindley-Milner type system, these 6 rules. It's really not that complicated. It looks scary, but once you understand the intuition behind it, there's really nothing to be afraid of. So let me dispel some possible confusion. What we have seen is a type system. It is the semantics of a type system. It is not typing algorithm. So we have seen a bunch of inference rules, and they can be used to prove statements about types. We've called these statements type judgments. We know that these statements are true because our system should be sound. What's not given to us, however, is how to prove the statements, which is to say which rules do we pick and when do we apply them. And to do that, we actually need a typing algorithm. And so for Hindley-Milner, there are 2 typing algorithms, algorithm J and algorithm W, and typically the practical one is algorithm W. These algorithms do have a close relationship with the underlying type system, and they indeed help with efficiently selecting and applying inference rules. So what have we learned in this video? Formal type systems usually work through the use of inference rules, which are used to derive type judgments supported by a set of type bindings. And we use these type bindings to make assumptions on types, which can then be used to derive more type judgments. Hindley-Milner, in particular, is a type system for the polymorphic lambda calculus. It only has 6 inference rules, and they enable the use of polymorphic types, in particular polymorphic function types. This is relevant in practice, as this is the theory behind the typing algorithm of Haskell, ML, and some other functional languages. We've seen 3 desirable properties for typing systems: decidability, which means there exists a procedure that can make a typing decision. Soundness, which is that everything the typing system proves is true. And completeness, which means that everything that is true can be proven. In the context of type system, decidability means that there is an algorithm that is able to eventually make a decision. So either the program is well-typed, ill-typed, or the algorithm can also stop and decide not to type the program in the case it's also incomplete. Soundness means that if the typing algorithm derives a type, this type is correct. It's never wrong. Completeness means that all program can be typed. If you have to give up one of these three properties, it's better to give up completeness, right? You don't want your program to assign types which are not correct, and you don't want your type algorithm to hang forever. Finally, pragmatically, one reason I like to talk about formal type systems is that the idea of inference rules has great practical applications even if you never write a formal type system. The idea is that you can take some premises, derive conclusions, and these conclusions can be used as further premises. This can be used to implement semantic analysis in practice, type system, but also the other form of analysis. And in fact, that's what we'll talk about next time, and we'll use the Uranium library that I wrote for that. I hope this video has been instructive. I wish you all the best. See you next time.